Well, special relativity does the job. We had a problem with speed with the too fast objects. And special relativity is the theory that explains how objects move when they are going very fast, like close to the speed of light. And general relativity is the theory that explains how gravity works and how objects move in a curved spacetime.
Hello and welcome everybody to a new episode of Your Friendly Physicist and Other Nerds, your science podcast where scientists speak about their fantastic research, their visions, dreams, challenges, and their daily life in the fabulous world of science. My name is Lucas and I am the host of the podcast Your Friendly Physicist and Other Nerds. A few weeks ago, there was a very first to-go episode where I spoke with Gian Inkof about the basic principles of quantum mechanics. And today's episode will be again a to-go episode, only this time it will be about the basics of special and later on general relativity. And I'm more than happy that again Gian joined me as an expert. So welcome on board, Gian.
Hello.
I'm very happy to see you again on this podcast.
Hello. I'm so happy to be here again.
Let me once again introduce you properly. So you studied physics and did afterwards a PhD in theoretical condensed matter physics with a specialization on holography. And last time you explained to me this is a mixture of quantum mechanics and general relativity. So the perfect expert for last episode, but also for today's episode.
Perfect.
Yeah. So, a short disclaimer before we start right into general relativity. We have a set of around 10 questions, whereas some questions surely will split up in a few follow-up questions. And the very first question will lead us to gravity. So, Gian, why are we starting with gravity? Why is gravity important for understanding relativity?
Yeah, that's a very important question. As you said, the theme of today is understanding a little bit about special relativity and general relativity, and gravity is the main theme of general relativity. And we always have to distinguish between what is the physical phenomenon we are talking about and how do we describe it. So the how we describe it is through general relativity, but the physical phenomenon for general relativity is mainly about gravity. So that's why we are starting with gravity. What is gravity? Well, the one-line answer is gravity is a force that pulls together the objects. And more specifically, it's like an attraction force between two objects with a mass. And well, if you think about it, gravity is the responsible for making an object falling down, or another huge impact of gravity is that, for example, planets can orbit around stars or around each other. So that's a pretty interesting topic in my taste. Well, if we want to talk about instead why is important to study gravity, we have a million answers here. A more theoretical physics answer, if you want, is because it's important to understand how universe works on the large scale, so again, planets and so on and so forth, but also to understand the structure of the universe. Gravity somehow governs the structure of the universe. But if we want to instead talk about applications of gravity, gravity has also very nice technological applications, like satellite applications is just about gravity and balance of forces and so on and so forth. But also GPS. The GPS we use every day for going from point A to point B on our phones is based on general relativity and gravity. So that's why.
Great answer. So I think in terms of general relativity, we are now more on the theoretical side, more on the universal length scales. So how would you say, are we describing gravity in a theoretical way?
That's another very important question. And it depends on the range you're interested in. But if you want to follow a somehow historical line, the very first attempt to describe gravity theoretically was made by Newton, Isaac Newton, As we discussed in last episode, we have the classical physics, which is governed by the laws of Newton. And more specifically for today's episode, the law goes under the name of universal gravitation law of Newton. That it is an expression, if you want, for the force that two objects with a mass exchange. As we said before, gravity is an attraction, and this is described by the Newton's universal gravitation law. But some problems may occur whenever in the physical phenomenon we are investigating velocities or masses are too high. There, Newton's law fail. So remember, in the quantum mechanics episode, we had a similar issue. We wanted to investigate the microscopic world there. We tried to apply the classical laws of Newton, and we failed. So there, we needed to introduce a far more general theory, which was quantum mechanics. Here we have an analog problem, but regarding objects that are too fast or too massive. Here, the correct way to generalize Newton's law is by introducing general relativity. But before even diving into the details of general relativity, we need to mention an important intermediate steps to GR, to general relativity, which is special relativity. It is a more elementary version of general relativity, but the point here is that gravity is not the main theme of special relativity. Gravity will be the main theme of general relativity, but we need to talk about the special one to get to the general one.
So actually the special relativity was developed before general relativity.
Exactly.
So maybe in a historical sense, when we talked a lot about the Newtonian law of gravity, so this classical physics was founded, I think you looked it up, 1687, so in the mid ages. It's a long time ago, but of course it's still valid. But we know, as we saw in last episodes, that there is a smaller world, like quantum mechanics, where classical physics cannot be applied, and now we are also limited by very fast and very massive objects where Newtonian laws also cannot be applied. So it's nice that, I mean, it's still valid, of course, but we found more marvelous worlds around where different laws have to be applied to explain the things that we can measure or that we can see there. So special relativity was developed by Albert Einstein in the beginning of the 20th century. What is special relativity? Simple question, probably very complicated answer.
Well, I will also here start with the one-line answer. And well, special relativity does the job. We had a problem with speed with too fast objects. And special relativity is the theory that explains how objects move when they are going very fast, like close to the speed of light. This is what special relativity does. But it has very huge consequences and also applications not only in this field we're talking about, but also more general, like in particle physics. You need to use special relativity to correctly describe particles, but also in electromagnetism, the correct way to phrase electromagnetism is through the formalism of special relativity.
So basically every application field or every science case where objects move very fast, close to the speed of light, you need this special relativity.
Exactly. Think about LHC at CERN. That is a particle accelerator, and their particles move very, very fast. And there you need also special relativity.
So now we know what is special relativity. So it's a theory in order to describe things that move very fast and also that are very dense. Or is this already then a thing that is described in the general relativity?
Yeah, it's more talking about general relativity takes into account also of the effect of big mass, let's say a gravitational or relativistic effects due to very big masses.
Then let's stick to special relativity for a few minutes more here. We already framed like gravity, but how does the speed of light now comes into play?
Yeah. Well, normally speed is something that it's not fixed. If we change the reference frame, speed is something that can change. So think about two different scenarios. You're sitting on the bench and you see a car moving, and say you measure 80 kilometers per hour. Whereas now you are driving as well at 40 kilometers per hour. This is another reference frame, and you will measure another velocity for that car, that in this case is 40 kilometers per hour. So in everyday life, we are totally fine with the fact that velocity is something that can change. Instead, in the theory of special relativity, the speed of light is constant. This means that it doesn't change by changing the reference frame. In other words, this means that the speed of light is a universal constant. But if the speed of light needs to be constant, that something else needs to change to compensate this. And for example, time will change, space will change, and even mass can change.
Maybe a short add-on question here. Do you know how this was proven? That speed of light is always a constant, a given constant?
Yeah. They're experimentally. They made an experiment with, I think, because this is for experimental physicists, I'm a highly theoretical one, so, don't trust my words. But essentially, through an appropriate physical device, which is an interferometer, I think, they could measure the value of the speed of light, and they simply simulated this, or not simulate, actually changed the change of reference frame, like by performing this measurement in different time of the year, so that the Earth was in another position, and so that the light could have come from a different angle. And it has been shown, observed experimentally, that the speed of light was the same. So after many, many evidences of that sort, Einstein said, okay, let's try to see what happens if I build up a theory where I have the speed of light as a constant, and let's analyze all the consequences of this assumption. And this incredibly matched the experiments for the upcoming years.
I think that was revolutionary back in the time in the early 20th century to assume that speed of light is constant, even though, yeah, as you said, you are maybe sitting on a moving planet and you send light out to somewhere. The speed of light won't change if you change, for example, the velocity of the planet you're sitting on, for example. So the speed of light will always be the same and will always be constant. But you said something very interesting. So speed of light is constant, whereas time, mass, space is not constant. So maybe we can go in a bit more detail here. Maybe we can start a little nerd talk. And this is something I wanted to do anyhow, and I even created a little jingle. So here is Nerd Talk. This was actually a question that came from our listeners who wanted to know what is this thing that is called gravitational time dilation. So it's something where time is not constant, or time is relative, so to say. Can you explain, maybe first in a basic sense, but then you can for sure go into a bit of detail, what this effect actually is?
As we said before, there is this tricky starting point of special relativity where velocity is something constant. And as we said before, logically, if velocity is constant, something else has to compensate, has to change for that. And gravitational time dilation is the effect of time appearing to pass more slowly when we are close to the speed of light or in a strong gravitational field. So this is like the basic definition of time dilation. So time perception varies depending on your velocity. If you are close to the speed of light, your time perception will be slower than if you're sitting on the bench. It's like you have a watch and you have the tick of your watch that signals the second flowing. Well, that tick will take more time if you are close to the speed of light.
Or in a strong gravitational field.
Or in Australia, I mean, I'm trying to use like some placeholder words because then we will see in general relativity that, yeah, we're talking about gravitational field there. This is a thought experiment if you want. First of all, I'm pretty sure to say that in order to reach the speed of light, you have to be as big as a particle.
Yeah.
Or, I mean, there are some technological problem, let's say, in pushing a human being at the speed of light, more or less. But let's assume we can. Let's assume we can. We just said that if we sit on Earth, our perception of time, our time flows differently if we sit on a spaceship that goes close to the speed of light. And this paradox tells us that basically, if we have two twins and we separate the twins, and one twin goes close to the speed of light, of course, he or she or whatever will age differently from the twin on Earth. But this is only, I mean, there are some technical details here about inertial systems and which are probably too technical here. And also in the interstellar film movie, there is something like that where there is the father, but I don't want to make spoilers here. But I would strongly suggest you to watch Interstellar because it's very accurate, and you can find something similar there.
I think it's okay to talk about Interstellar. The movie has been out there for quite a while, and
yeah, okay.
But so if you want to go into more detail, I mean, we're still in the nerd talk. This would be the chance to do so. So this short disclaimer to the listeners: if you don't understand everything during the nerd talk, you will still be able to follow along also when the nerd talk ends. So this is just a new theme in this podcast, since it was also suggested. So this was kind of feedback from the community, and I really like that idea. So that was the gravitational time dilation. A next question, which I really would like to know in a detailed manner, if you allow, is what is the equivalence principle?
Yeah, this is a very subtle question, and you have a very interesting followers, Lucas. So
at this point, thank you to Daniel and Connie.
Yeah, thank you so much. Equivalence principle is again at the basics of what is gravity, even more. It doesn't relate just only to general relativity, where there are different points of view on that. Indeed, it has very different formulations, and maybe we spend a few words about it later. But essentially, the equivalence principle is the concept that states that the effects of gravity and acceleration are the same, indistinguishable. So in principle, one can think that gravity is something different from acceleration. But if we follow the Newton's reasoning, and we just said that gravity is a force that pulls together objects, but it is a force. And in Newton's laws, the force, or better, the sum of the forces is equals to the mass of the object times the acceleration. So if we know that basically a force is proportional to the acceleration via the mass, maybe we could have something similar also for gravity force. And we know that a version of the gravity force is simply that the gravity force is proportional to the gravity acceleration, g, with the letter g, through a constant called the gravitational mass. So the equivalence principle states that the gravitational mass is equal to the mass that appears in the second Newton's law. This is like a little bit more technically what this equivalence between the effects of gravity and acceleration mean. More generally, maybe more into the general relativity language, equivalence principle states that it is always possible to find a reference frame that where gravity is null, is equals to zero. When you are into a gravitational field. because this means that you can engineer, if you want, a reference frame, which simply means a system that moves with a certain acceleration in order to cancel the effects of gravity. So if you're able to cancel the effect of gravity, then you know how to govern it. This is basically, I think, goes under the name of strong formulation of the equivalence principle here.
Is this, I mean, is this only a theory, or does this also have practical application?
I would say this is more about theory, because then you unify two properties that you thought you were different into a single one. Yeah, but actually there are also practical applications, like the absence of gravity experiences, like in shuttles or stuff like that, or also like in simple parks games, where you cancel the effect of gravity through an acceleration. Things you are on an elevator, for example, and this elevator accelerates a lot, then you could experience the absence of gravity. And in some sense, this has a maybe not applications, but impact also in everyday life.
Like in a free falling tower on.
Yeah.
Then you get rid, in quotation marks, of the gravity by
Exactly.
creating an acceleration towards the Earth.
Exactly.
Yeah.
But in this sense, you cancel gravity, so through acceleration. So
Yeah.
they must be similar effects
Yeah.
or sibling effects.
Yeah. And this can then be used to further develop theories and models and so on.
Yep.
Okay, I see.
Precisely.
Great. So I think enough nerd talk for gravitational time dilation and equivalence principle. Let's finally come to general relativity. I think we are now ready for this term. What is general relativity?
Yep. Well, I can't tell you without introducing a basic object of general relativity, which is the space-time. So let me spend a couple of words about that. Otherwise, we are getting lost. So we are all familiar, I hope, with the fact that the world is three-dimensional. So we have an X and Y and a Z direction, and we are free, more or less, to move in this three-dimensional world. Well, Einstein had a very revolutionary ideas, and he said, well, let's say we don't have three dimensions, we have 3+1 dimensions, where the plus one is time. So Einstein already started thinking that time and space are tightly connected to each other. And this is something that it's a generalization of what happens in special relativity, where time and space kind of change to keep the speed of light constant. So first of all, we think about 3+1 dimensions here. And we call this the space-time. So the space-time is an object we are moving in, like think about a medium, we like an ocean, where we also have the +1 dimension, which is time. Exactly like the ocean here, we don't have a flat object. We have a curved object with ripples. And how can we produce ripples? Well, with mass or with energy. Maybe here an image can help. Let's think about that we have a stretched sheet, and we can curve that sheet by placing a heavy ball in the middle of the sheet, and then we have a curvature. Now we throw a marble, and this marble will start orbiting around the central ball by following the curvature. Well, at the same time, the idea of Einstein was we have this space-time which is curved by the masses, and gravity is an effect of curvature, is a consequence of curvature, exactly like in the picture we just evoked. And well, for example, as we will see later, black holes are extremely massive objects, and close to a black hole we have a high gravity, a high curvature, and here we expect gravitational effect to be extremely pronounced. So to answer your initial question, general relativity is the theory that explains how gravity works and how objects move in a curved spacetime.
thinking back to our last episode, I think we mentioned there that this is a theory that is still ongoing. Can you comment a bit on that?
Yeah, sure. It also depends on the here on the length scale of the phenomenon you're considering, because general relativity is extremely good whenever you want to talk about phenomenon happenings on large scales, like planets or even more galaxies and stuff. It is extremely good. As we will see later, we are able to explain many universal and physical phenomena through GR. The problem, of course, whenever we wanna apply general relativity to the atomic scale, or even a little shorter, there general relativity fails. For example, there is a well-known fact that um, it is hard to imagine what happens behind the event horizon of a black hole, where basically there is a singularity, which is a point-like object hidden by the event horizon, and we don't have predictions there through general relativity. We would love to merge quantum mechanics, which is super good for this microscopic world, with general relativity, but we're still looking for the theory of everything here.
Yeah. Okay. Then I understood it correctly. Okay. So, I mean, general relativity, super long length scales, galaxies, the universe, space-time, black holes, speed of light. This is something that might not be around in our daily life. Are there concrete or specific examples of general relativity in our day-to-day life where we can use general relativity for useful things?
Yeah, definitely. So I think that the most well-known object is a black hole. We also got a picture of a black hole in the past years. Super fascinating. Well, a black hole is an object with such strong gravity that nothing, not even light, which is the fastest object in the universe, can escape from it. Black holes exist because they are formed when very massive stars collapse. And if something goes into a black hole, it gets pulled in and crushed by the immense gravity there. So that's what a black hole is, and it is beautifully predicted by the laws of gravity, of general relativity. Sorry, and Einstein at first, when he found the solutions of Einstein's equation, thought, "Well, I did some mistake. That cannot be true." But it's true. So this is one beautiful example of general relativity. Another one you might have heard of is gravitational waves, where that has been detected years ago, not too many years ago. But as I said before, the space-time is like a medium, is like the ocean. And exactly like in the ocean, we can have waves. And a gravitational wave is a ripple in the space-time that happens when two massive objects like black holes or some specific type of stars collide and merge. Like there is a dance where the two black holes rotate around each other, gets closer and closer, and then they merge into a single object, but there is a release of energy that creates this ripple in the space-time. But this is a ripple also of time, so it comes to you affecting the perception of time in a sense.
So it ripples the space-time, so space and time.
Exactly.
So this medium,
Exactly.
it ripples the ocean. So the waves in the ocean
Yeah.
are not only rippling the space, like in the ocean, but also the time, which is not happening in our oceans on Earth, but in the space-time in the universe.
Exactly.
That's so fascinating.
Yeah. And even more fascinating is the Einstein-Rosen bridge, or also known as wormhole. And that is an hypothetical connection between 2 points in space-time that could potentially allow for faster than light travel. So we are used to think that the shortest path between 2 points is a straight line that goes from A and B. This happens in flat spaces. But if we have a curved space, we can have all kind of stuff, and curvature allows like for the existence of in theory this, because it's still work in progress, but of connections between points that are very far apart, but curvature allows them for being connected.
Maybe in some near or far away future, we might use this Einstein-Rosen bridge for interstellar travels at some point.
Yeah,
maybe
get comfortable in the meantime.
Probably, yeah. Probably in the far future. But yeah, hey, that was a great. But I mean, it was a great historical guide from Newton, who in the 17th century also could have not imagined what we would have achieved in the 20th and the 21st century, with first special relativity and then general relativity. So that was a very nice and a very detailed and very, even though that's an audio podcast, I think you created some visuals in the heads of our listeners. I hope
too, and thank you so much.
Yeah, Gian, that was fun talking about general relativity, speed of light, gravity, and everything else. Thank you so much for joining me once again on this podcast. Who knows, maybe at some point you have a third episode. Let's see. And until then, thank you again. Take care and bye-bye.
Bye-bye. Thank you for having me.
That's it for today. If you have any questions left to Gian or me, just let us know in the Spotify comment section below or reach out to me either on LinkedIn or Twitter. If you like this episode, you might also like the previous To Go episode where Gian and I talked about quantum mechanics. And in the end, just one thing, this podcast is about you and everyone can participate. So if you or some of your friends want to share an exciting story about science, your academic life, crazy experiments, or any other nerdy stuff, feel free to drop me a short message. Thanks for tuning in, take care, and see you soon on the next episode of Your Friendly Physicist and Other Nerds.